Welcome to the morning session on Tuesday. We have 6 presentations. First presenters from Poland, Professor Bogdan Miziński, please.
Okay, thank you, Mr. Chairman, ladies and gentlemen. I think that not too many people as today, but it's obvious that means that yesterday we enjoyed very much. Okay, but thank you for coming here. Okay, my presentation title is indicated here and deal with the problem with detection and selection of ground fault in the network, middle voltage network, mostly in the middle voltage network which operated in mine, or open cast mine, which is very important things, with no effective earthing. The first is introduction, next the general concept and of the protection, sensitivity problems of the protection, shielding on three-phase cable load interference, performance of the protection on the ground faults in real middle voltage networks, no effective grounding, and the conclusions. As I already mentioned, we have a real problem with the clearing faults in the ground, particularly when we have heavy resistive faults. Therefore, in this case, there's no way to detect it, since everything depends on the resistance or impedance of the loop through which the current is being flowed. And therefore, practically, it's impossible to detect it, especially if this faults of a small current value, even below 1 amps. Due to security, we have to switch off as quick as possible. Therefore, that's very difficult to do that. And therefore, we use different protections and different methods and different way of operation of middle voltage networks. You know that the networks with no effective earthing can work as isolated, can work with compensated, can work with grounded via resistance, and can work also via grounded by impedance. And also we call this so-called compensated with additionally forcing of active component, which improve the operation of ground fault protection. Therefore, we are looking for another possibility. There's no problem of digital protection. Digital protection is a very good works, but only if you have the physical quantity when you measure it. That's the main problem, is how to measure physical quantity. That's everything. Digital processing is very easy, but the most serious problem is to detect this quantity, to measure this quantity as quickly as possible and with as high accuracy as is possible. We found out that one super problem as a choice can be used appropriate types of the current transmitters in the Hall sensor. Hall sensors for everybody is very clear what it is, and is widely used in the practice. And we found out on the basis of our experiments, which was done not only theoretically, but also we check it in a mine. And therefore, there is real possibility to construct such a sensitive switch. That's a very, very simple and can be easily adapted to the dimension of the power cable. Therefore, can be located directly on this. Here is the structure. The structure is very simple. There's a simplified scheme. As you see, that's the first is a core balance transformers, and for this case we don't use a residual current transformer. Residual current transformers were the 3 current transformers connected in parallel, but sensitivity is very poor. Therefore, the best is so-called, we call it core balance transformers, which sometimes we call Ferranti transformers. Therefore, that's this things is. Inside this is a gap, and inside the gap is located Hall sensors. And Hall sensors is activated under the influence of the magnetic field, which is generated by the current flowing in this. This is a zero sequence component, and then is polarized by the voltage. And the voltage, since it is directional protection, the voltage is used as the zero sequence voltage, which is taken from open delta unit of voltage transformers. That's activated units with fiber optics, whatever you wish. And therefore, it depends. You can use the wire or wireless transmission depending on the choice. However, here is already, I will explain you, is already inside. There's an additional core, which we call a screen. Just a moment, you will see, and also can be used additional windings that is also used to to supply independently this protection. As you see, the core is very flexible, is made of a sheet. Therefore, we are easily to clamp it on the cable, depending on that. Okay, therefore the principal operation is very simple, since this is based on the fact that we have a sine wave of a current and a sine wave of a voltage. Therefore, the flux, which is depicted here, is also indicated sine wave. Of course, include the high harmonics, and polarized current with proportional to the voltage. U0 is also sine wave. Therefore, the whole output of the whole is a product of these two quantities. That's the parameters you see factored depending on parameters of zero sequence filter, voltage filter, and Hall sensor respectively. Here, as a matter of fact, after the introduction, internal angle you see, and the transformation, we obtained these things. As a matter of fact, we have two components. The whole voltage is composed of a DC component and AC component, and we use a DC component, just only DC component. Therefore, since it's very difficult to consider the phase angle, therefore to calculate it, we compare the DC component to the maximum AC component, and this way we have a calculation of these things. One of the problems that I would like just only mention is a slight asymmetry of Hall sensors depending on the structure. Sometimes we have fluctuations of AC voltage. AC voltage, as you can see here. Therefore, however, since we use a DC, it doesn't disturb our work of these things. Also, that's very important is magnetic properties of the core balance transformers. In this way, we employ this magnetic materials. This is a cold rolled sheet, and that's a magnetizing curve, as you see here for this when we employ it. First, we check how high is the magnetic field intensity or flux density in the gap, which is just a moment, in the gap here. Therefore, we just make the analytical attempt to that. That's a magnetic flux line distribution for the 2D, for the very small current I30, the 2 MEC, and the picture, the colorful picture for the same things. You see that there's some value of magnetic field intensity under which is located the sensor. And then next we consider the influence of the different parameters, geometrical parameters of a core balance transformer on magnetic flux intensity or density, and therefore depending in this way you can and these things this is not especially convenient to this. In these things you can find the flux density inside the air gap depending on the width of a core for this and this. For 50 amps, for example, you see that it doesn't depend it. However, of course, this is what is obvious. It depends tremendously on the gap of the gap length. What is obvious? Next is we check the flux density within the gap area as a function of the unbalanced current. I mean the Z3I0 for these parameters, and you can see that indicate the linear independence. Depending for this area. Therefore, this is linear, this is not linear. Therefore, we have also some problems here. Next problem is if the core balance transformer is too big with compared to the cable. Therefore, the location of the cable inside this inside the window of the core balance transformer can influence magnetic field intensity or flux density is here. Therefore, we checked first. We theoretically consider what's going on if we have a different asymmetry and different location of the three-phase cable, and we check the value of magnetic field flux density or magnetic field intensity inside, and we found out that that is real problem. That's a real problem since if we want to get the very sensitive protection, therefore we have to protect against this problem. Therefore, what we decided in this case to use additional screen. The cable is surrounded by the additional screen made of the same materials. And what is the influence of these things? First we make a calculation since it is symmetrical things. Therefore, we can consider it just only for the half of the system. That's you see in this way. There's a core balance transformer. There's a screen as a three three phases respectively here, and then we consider that's a gap in which the sensor is being located. As a matter of fact, we found out that sensitivity, the magnetic flux density inside the core balance transformers in which the Hall sensor is exerted, depends, of course, of the thickness of these things. Therefore, for this thickness like that, there's not any influence. There's not any influence about the D over DC. However, with increase of the thickness like that, we have some influence of that. Therefore, the more higher is the thickness of the screen. Therefore, the lower is the magnetic flux density. Therefore, sensitivity is being dropped down. However, if we compare S and R, signal noise ratio, we get a better relationship with the screen than without the screen. Therefore, the efficiency of operation is much better. If was already done, it was just calculated, then was investigated using the physical quantities. Therefore, we make investigations in the real mine, copper mine conditions. No copper mine by brown coal conditions. That's why this is network structures like this. It is supply, and here in this network you can see different level of middle voltage. For example, in this mine was 20 kilovolts and 6 kilovolts, and you know that if we have Y delta transformers, therefore delta act like a trap. Therefore, there's no way. There's no round for the current flowing there. Therefore, if we have a faults therefore the current is flowing just only this way. So, not if you have a fault in the 6 kilovolt, the current is independently. I'm talking about the ground, fault to the ground. In this case, for the 220 kilovolt, the networks operated with isolated neutral point, with also with a grounded neutral point. However, for the 6 kilovolts, it was compensated with so-called the forcing of active component. What does it mean? That if we have a signal from the voltage, after 3 seconds, you know, this switch is being closed, and we include resistance. Therefore, we force additional resistive current value, which is very good for the active. For the protections, indicating active parameters. And then next, you see that's indications of the measurement and real mine. And then in this case you can see the picture for the this is a fault. Fault is in this point, this ground fault. After 3 seconds, we have automatic forcing of active component forcing. Therefore, the current is being increased in this point. And as a matter of fact, immediately we have a picture. Here you can see that for this way, then we have a compensated. However, the sensitivity of the whole sensor this is the highest when there's no shift between the current and between the voltage. We have to use some shift. And then the shift is for this compensated must be 90 degrees. Therefore, in this case, when you see that even that we have a fault where we have no forcing of the active component, the value of DC component of whole sensor is very little. And this moment is raised up to about 5 volts, and therefore that's here. And therefore, you see that for this system, after activation of ACV, the network, we are able to detect this fault easily. This is an example that you can see that for the 20 kilovolts, however, totally isolated for the current between 0.3 and 1.5 amps. That's very little current. It's very difficult to detect it. You see that the current for these things is the voltage DC is pretty good. It's about 2 volts, something like this. Is saturated to about 1 volt. Therefore, easily we can detect these faults. Here is an example show you the performance in the 6 kilovolts networks. This is absolutely similar, the same. As you see, this is there's the ground fault. There's an operation of ACTV. Current is being increased. You can compare it, and that's worked very good. And here you see that's operation like you can see. This operation, there's a DC component, the whole that is for after the operation ACV, this increase of current. These are like the step things in the current This not force exactly the same. Probably the loop resistance is being changed. Therefore, once is increased a little bit and another is increased about the 20 amps. And here is indication, since we located this protection not only on the photo lines, also on the healthy line, to compare what's going on the healthy line. On the healthy line, you see this. We also obtained the DC component, however, is negative. This blue line is, you see, there's a negative, since the current flow is just opposite direction. Therefore, you see that this protection we found it can work very good, provided that properly selected, properly designed. Any conclusions? There is a chance for use the Hall sensors as a sensing element of directional earth fault protection for medium voltage power network with no effective earthing, provided the proper selection of a new structure of a zero balance current transformer. At the criterion for protection, we use the DC component of a Hall voltage as a result of product sequence current and the voltage affecting the sensor. However, to increase resistance of the protection to internal electromagnetic fields interference, therefore of asymmetry of load as external interference, special magnetic screen must be applied. And investigations which were carried out under real ground fault protection for different faults, solid earthing, high resistance up to about 2.5 kilo ohm. Earthing we perform it by dropping the line of the overhead line to the ground and allow to just freely allow the arc freely the things. Therefore, the current in this case was very little, and with high resistance up to about 2 kilo ohms and 6 kilovolt and 20 kilovolt distribution with no effective earthing, confirm applicability of this sensor. This protection is easy to use, maintained, and managed. Thank you very much.
Thank you very much. Interesting presentation. Any questions? Yes, please.
I have one question. Generally, concerning the theory that clamping this high voltage cable, I'm just wondering, I guess this is relatively common methodology to use a clamp for that purpose. And generally, when using clamp, this is practically very similar to current transformer in the overall. So I'm wondering what is the advantage of this approach with Hall sensor, considering that we have seen that you had a problem with the position of cable and the flux distribution inside when you use the element method to check it. And what is the comparison between this method with Hall sensor in contrast with, let's say, the current transformer approach?
Okay, thank you. I think that you know how it look like the Ferranti transformer. Ferranti transformers are big things like that, and the size of this, there's a big things. Therefore, we use very little, and we clamp it directly on the cable. Therefore, the magnetical coupling is as high as possible. We consider this asymmetry due to the situation when the window is a little bit bigger. Then, since not necessarily you have to use the Hall sensor protection for the particular cable, sometimes you select it. That's the main advantage. That's absolutely main advantage. That's all. That's all.
Fault detection in a medium voltage network may be realized according to various criteria. It depends on the type of earthing, through resistance, through Peterson coil, or isolated. Is your method dedicated to the network with isolated neutral point, or maybe earthed through resistor?
Both. You know, that's only we have to use a phase shifter. This phase shifter was indicated here. Wait a moment. That's just a moment. Oh, this is a phase shifter. We have to change angle. Since sensitivity of Hall sensors is the highest when we have current. I mean, zero sequence current and the voltage in phase. However, as you well known, it depends on the operation of neutral point. Yes, yes. Therefore, we have to shift about the 90 degrees. And of course, we compare the efficiency of that with the different types of protection. Overcurrent protection, delay time, admittance protection, everything. And we get that that seems to be the better.
Thank you very much.
Thank you.
Thank you.
Thank you.
Okay. Next presenter is from Czech Republic, Mr. Václav Kolak.
Okay, Mr. Chairman, ladies and gentlemen, good day to you. My name is Tomáš Mlčák. It's good. I am from VSB University, Technical University of Ostrava, of Czech Republic, Faculty of Electrical Engineering and Computer Science, and Department of Electrical Engineering. I introduced the article improving power quality with the use of a new method of serial active power filter control. The quality is still very discussed issue, and we three nonlinear loads in supply voltage distortion in distortion gate width is due gate in impedance. This picture show the main indicators of quality of electric energy. This is amplitude of power voltage, frequency for power supply network, voltage drops and overvoltage, harmonic distortion and flicker, and voltage asymmetry. In other picture show this hardware conception in this serial active power filter. This is converter. This converter is directly show this UC voltage, and this voltage sum with voltage from line US, and this is transformer. This sum with US voltage we have this voltage UL. This is filtration voltage. In other picture we have which we can be used the serial active power filter. We maybe compensate the voltage drops and from the power supply impedance. We symmetrate and regulate power supply voltage, filtration, harmonics. We maybe causes is US, the power outage, and we maybe regulate this phases shifter. In this we use some three methods. One method is Butterford filter, successive fourth order approximation, and fast Fourier transform, and new comparative method we developed with author. This is first method controlled by Butterford filter. We here first Clark transformation and other reverse Park transformation, and this is low pass Butterford filter fourth order, and then we have Park transformation and Clark transformation, and can calculate voltage for the converter for the power filter. This is equation for this model for microprocessor and by linear transformation. And this is second method. Second method is fast Fourier transform method. We sampling some values and calculate Fourier transform. We calculate these amplitudes, and now we have this UC signal for converter. This is fast Fourier transform from example from 4 point of discrete Fourier transform, and this is no good, and this is no better, because we must sampling this value, and after we calculate this distortion. It's some next time. It's here is other method. This is author's method. In author's method is comparative method. We have in microprocessor this sinusoidal wave, and we comparison this sinusoidal wave from this wave the phases. This is very good for a serial active power filter, because we now ended voltage. We have 327 voltage and 50 hertz. This is possible. This calculate directly. Here we can see pictures is from block diagram, connection, measuring, and control system. Here is phase loop loop. Here is voltage science. Here is block generate. This is block DC low voltage measure, and this is analog digital converter, and is block set pulses for this converter. This is signal microprocessor for control all system. We measure this with some distortion voltage. We take here some inductance, and here we destroy supply voltage. First from three phases rectified, and other is one phase is rectified. That's other example. Here is distortion voltage, and here is measure for this system, and we sum this UC in this system, and here is sinusoidal output for these loads. This picture show harmonics in the system when voltage distort by 3 phases rectifier and resistive inductive loads. This is total harmonic distortion from power supply, and this is total harmonic distortion from Butterford method and Fourier method and comparison method. Yes, this is show that this comparison method is the better, and here is some each harmonics from this measure. Yeah, this is waveform from this measure. Here is control using comparative method and inductive load, and input voltage is destroyed by 3 phases rectified. This is input voltage in the serial active power filter, and this is output voltage. This is control voltage for converter voltage you see, and this is show the same, and the voltage destroyed by single phases rectifier, and this is input voltage and output voltage. Here show some nesymmetry, and each phases distorts other, and here is look here we can see output voltage from the serial active power filter. Yeah, in conclusion, we tried that this comparative method is the best method for using this this serial filter, and this serial filter we can use for extensive distribution geared, where we use this is low cost from this we building new network or new gear. We use for off-grid systems, and some modified this we maybe used for some system which where we accumulate many energy, and then we cover system by voltage from serial active power filter. And now we testing some combination serial and shunt active power filter in hybrid filter, when shunt active power filter eliminate this first problem in this distortion in the system power voltage. Yeah, this is all. Thank you for your attention.
Questions?
That's very interesting, but did you also perform the compensation of active power? Compensation to compensate reactive power, since you know that's not easy to do that when you have distorted current and voltage waveforms. And so far, the theory about the power is not fully understood. There are many different. Few years I had a presentation, white paper, showing about the problems of the active power filters. That's please take care about
this reactive power. We must calculate this very many loads from this.
But it's not easy. It's not easy, you know. That's please look at the literature, since the theory doesn't exist. So far, there's no
It don't have
explaining this
model, and we must calculate quickly from this situation.
No, it's not the problem of how speed it is. There's the problem how to do that. Nobody knows how to do that. There are few theories. We use one of the theories, Charnetsky, Professor Charnetsky, that is theory of instantaneous current theories. Therefore, since the reactive power, which is carried out by high harmonics, it doesn't complain. You know, that means that sometimes they explain that this energy is split sometimes in the system. Therefore, it's not easy to use such a active power filter just for compensation reactive power when we have distorted current and this waveforms. Of course, we can filter everything, but another problem is the compensation.
Okay. Okay. Thank you.
More questions? I have a question. Your filter is a serial filter. Could you say something about power losses and voltage drop in normal operation, because the filter is still in main circuit?
Yeah, we measure this efficiency of this filter. This efficiency was in the 30 to 85%. You say that this filter not working in the nominal, but in working sometime in the 50-30%. This efficiency, this is other problem. This efficiency is lost. This cases. Yeah. Okay.
Thank you very much.
Okay. Thank you. Bye.
Is from Spain. Carlos Roncero Clemente, please.
Well, thank you, Mr. Chairman, for your introduction. Thanks for coming to everyone. My name is Carlos Roncero. I come from Spain, but nowadays I'm working at the University of Lisbon in Unova University, and I'm going to present my work entitled New Operation Strategy for a Grid-Connected Three-Phase, Three-Level, Neutral Point Clamped Quasi-Sector Inverter based on power losses. The structure of the presentation will follow the next scheme. First of all, I will do an introduction in order to delimit our topic. After that, I will explain step by step the design of the grid-connected operation strategy of our power converter. After that, and once has been defined some guidelines, I will propose the operation strategy to be implemented, and to validate these ideas, a simulation study was performed with the discussion of the main result, and finally the conclusion and the future activities. Nowadays, it is well known that shortage of fossil fuel and the necessity of reducing CO2 emission, among other reasons, has significantly grown the number of inverter-based distributed generators connected to the low voltage distribution network. Many of these converters interact and perform as interface with renewable energy source like PV panels, wind turbine, and also they are presented in any energy storage system. One can assure that this power converter will play a major role in the future smart grid. Concurrently, industry and research are aiming at cost reduction of the overall energy conversion process, and some innovative ideas looks pretty interesting for the photovoltaic energy conversion system. Traditionally, this conversion process for photovoltaic energy has been composed by two-stage power converter, a DC-DC boost converter, and a traditional inverter, and some new topologies based on impedance source network can step up this input voltage in a single state by means of the shoot-through. The main problem is that the relatively youth of the impedance source inverter make the design of their controller stage complex, because we can see here how complex is the input stage where many poles are presented. In a grid-connected converter, basically must coexist an operational strategy for the AC side, the synchronization, of the inverter, a DC-link voltage control method, and special modulation techniques for this particular family of inverter in order to embed the shoot-through stage into the normal ones. As basis idea, we started to develop a control strategy based on conventional synchronous generation principle, based on the well-known relationship between the active power and the frequency, and the reactive power and the voltage. Based on the main equation and assuming that the angle between the generator voltage and the grid voltage is near to zero, is very small, we can determine that the degrees of freedom to regulate active power and reactive power is the delta angle and the generator voltage, and also the generator voltage is the degree of freedom for the reactive power. Making an analogy with the equation that governs our impedance source inverter, we can include new terms in the degrees of freedom, the shoot-through that is cycle, which can increase the generator voltage. And even if we use some special modulation techniques, which can include the third harmonic injection, we have also a new degree of freedom. So in order to discover or trying to look for the best magnitude to control is necessary to establish some criteria. Our criteria will be based on the power losses, to minimize the power losses, but we have to assume some particular feature of this converter. For instance, the reference active power usually is given by a maximum power point tracking, and there are different approaches to generate the reference of the reactive power, for instance, to work with a constant power factor, or to maintain the voltage at the point of common coupling in certain values. Of course, we have to assure that the maximum rate current across the semiconductor must be respected. How to track the reference of the reactive power? As we have seen in the previous slide, we have different degrees of freedom, and we have divided the operation range depending on the input voltage. We have, for instance, that the input voltage can be higher than 650 volts, so we can or we have to work in back mode with our converter when the input voltage is between those values, in this interval between 565 volt and 650 volt. We have to work in boost mode, and if the input voltage is even lower than 565 volt, the input voltage must be, the operation mode must be even the boost one. This control variable will be discussed based on the power losses. Here we have seen the main simulation result based on the power losses. For instance, we have here the main limit between the different intervals that is necessary to be studied. When the input voltage is higher than 650 volt, we have different combination. But according to the whole efficiency of the system, the best way to operate is without shoot-through, that is cycle, without shoot-through state, without third harmonic injection, and just modifying the modulation index. We will work with the highest values of the modulation index. In the next interval, it's necessary to boost the input voltage, because we cannot connect our system directly to a 325 peak volts distribution network. And the best way, the optimal way to operate is by injecting the maximum value of the third harmonic injection and also changing the modulation index. When we get this value, 491 volts, we cannot perform properly our system, and start to be necessary to boost the input voltage by means of the shoot-through stage, and we can see how the efficiency decreased in quite high weight. Adopted criteria based on this analysis is to minimize the power losses that are composed by switching, conduction, and turn on and turn off losses. Here we can see the implementation scheme of our power converter. we can see how with the delta angle we regulate with a simple integral controller the referent power, and the reactive referent power can be tracked by different approaches depending on the input voltage range that we can find. In the first case, when the input voltage is higher than 650 volts, the variable to control is the modulation index. In the next interval is also the modulation index, but we inject the maximum value of the third harmonic. And finally, we have to control the shoot-through duty cycle if the input voltage is lower than 550 volts to obtain the maximum boost capabilities. Here we can see the main switching, the main signal in each modulation techniques without third harmonic injection and without shoot-through. Here without shoot-through and with third harmonic injection, and here with third harmonic injection and also shoot-through. Now we are going to present some simulation results that validate the previous operation strategy. We modify the reference in both the active power and in the reactive power, and we can see how our system tracks properly the different reference. For instance, in second 2, we change the reference power from 2 kilowatts to 3 kilowatts, and in second 3, we change the reference of the reactive power from 0 to 0.5 kilovolt ampere reactive. This is the same test that we have done in any input voltage interval. In this case, we can remind that the control variable, the degree of freedom that we are controlling, is the modulation index and also the delta angle for the active power. Here we can see the evolution of both magnitude, and here we can see a detail in this last time of this test, and we can see how the current is shifted in comparison with the grid voltage. The DC link voltage is higher than 650 volts, and also the input current and the input voltage. We can see how the input voltage is working in continuous conduction mode. In this case, the results are quite similar. Our input voltage is located between those values, between 565 volts and lower than 650. And again, both reference of active power and the reference of reactive power are tracked successfully by means of the modulation index and the evolution of delta angle. And finally, in the most critical case, when the input voltage is lower than this value, in our case is around 490 volts, we can see how the system again tracks properly each reference, both the active power and the reactive power, by means of controlling the delta angle and the shoot-through duty cycle. Here we can see how the grid voltage is distorted because we have connected our system to a low voltage distribution network with a high impedance. The short circuit power of our grid is quite low, and we can see also this distortion is produced by the ripple in the shoot-through duty cycle, and this effect in the DC side are transferred to the AC side. This phenomena is quite common and is well reported in the literature. So in this case, we can assure that the system performs properly, but the quality is a little bit worse. As main conclusion of this work, with the proposed strategy, the overall system performed properly. Active power and reactive power response are coupled because the delta angle also, the generator voltage also affect to the generating active power, but we assume in the equation some assumption. When the shoot-through duty cycle is applied, output magnitude are distorted because this ripple and are transferred to the AC side, and further research will improve this control strategy mainly by using DQ reference frames in order to control DC magnitude, and of course we are dealing right now with experimental work in the labs. Thank you very much for your attention, and if somebody has any question, please. Yeah.
Have you verified your stuff in laboratory condition, or is it still in modeling simulation stage?
Yes, we've already built some prototype, and we are starting right now with open loop test. We are just connecting the converter to passive loads and testing, for instance, the modulation techniques, and the next step will be the synchronization with the grid connection with the grid, and step by step we will try to validate this strategy and other more that we have already proposed and developed in a real system at a nominal condition as well.
More questions? Thank you very much.
You are welcome.
Next presenter is from Poland, Mr. Joachim Piet. Sergiu Goran. Sergiu Goran, yes. Sorry.
Thank you for the introduction, ladies and gentlemen. I represent Faculty of Mining and Geology from Silesian University of Technology in Gliwice, Poland, and the title of our work is Empirical Model of a Human Body Resistance at the Hand-to-Hand DC Flow. Just shortly the presentation plan. After the introduction, I will present the aim of our research, how we measured human body resistance, what model we implemented of body impedance, or we should say resistance, because we are talking about DC current. We identified the parameters of the model. It was used to evaluate later the maximum shock duration depending on the resistance, depending on the touch voltage, and at the end I will present some conclusions. It's well known that DC electric shock is less harmful than electric shock from alternating current. The number of accidents after DC electric shock is much lower. That's not only because it's less harmful, but especially it's the applications of DC are much less common than of alternating current. However, the number of DC application increases also for non-qualified users. I mean photovoltaic systems, which are widely used, especially in some countries. Power converters, electric traction. As I mentioned, I work in the Faculty of Mining and Geology. The application of power converters is increasing in underground coal mines with DC intermediate circuit, sometimes very long. Also electric traction, it causes a lot of problems because the trolley wire is relatively low. It's about 2 meters, 20 centimeters above the ground. So there are some accidents because of touching trolley wire. So we can say that the hazard of DC shocks is rising. The main two factors affecting the effects of electric shock is, of course, the duration of the shock and the magnitude of touch current. The touch current depends on the touch voltage and resistance of the shocking circuit, the whole shocking circuit. Especially in this shocking circuit, we can find two main resistances. It's the body resistance and stand resistance, I mean shoes and floor, etc. Of course, also the type of the current is important. When we are talking about AC current, frequency is important. I mentioned that because in our future plans, now we concentrated on the DC current. We want to do similar investigations for high frequency AC currents. Important is the current pathway through the body and of course physiological condition of a human. There are differences between individual humans as far as the body resistance is concerned, as far as the effects of electric shock are concerned. The aim of research was first to select a model for human body impedance. We have a lot of models described in the literature. We selected one of the models. Then, as I said, we identified the parameters of this model, and we found a correlation between maximum allowable duration of the shock and the touch voltage. It can be important from the requirements for means of protections point of view. For example, automatic disconnection of the supply. The time the supply should be disconnected after the fault when we have touch voltage, for example, on exposed conductive parts. The first model we found was in IEC 479 report, effects of the current on human beings and livestock. This model consists of series of impedances, impedance of the skin and the internal impedance of the body. Of course, the impedance, especially impedance of the skin or the resistance of the skin, depends on the voltage. We use another model which was described by Professor Korniluk from Poland. In some ways it's similar. We have this internal resistance and we have the impedance of the skin. Especially here it's worth to see this resistance depends on the touch voltage in exponent way. For the DC application, we simplified this model. Internal resistance, the skin resistance depending on the voltage, and the capacitance only for transient states. This is our laboratory stand. This is how it looked like. It's already prepared to do investigations of AC high frequency currents. We have voltage sources. These are two plain electrodes which were touched with hands with open palms. To keep the force of the contact constant, we used a digital scale. Then we have some recording system and measuring instruments. This is one of my colleagues, which was the subject of one of the subjects of the tests, and the subject was standing on the insulating matting to prevent the current flowing to the ground. And this is the block diagram of our measuring system. These are measurement results of touch current against the touch voltage for three different subjects, three males in the age of 40-50 years old. And we try to, this is values of resistance, measured resistance. We can see that, of course, the touch current is not non-linear to the voltage, and it means that, of course, the body resistance goes down as the touch voltage goes up. And we try to approximate values of the resistance. We use this mathematical description of the relationship between the body resistance and touch voltage. Here we see the touch voltage and the exponent. We try to find, we have three variables here, this coefficient, this exponent, and internal resistance of human body. The criterion we used to find these parameters was minimizing the residual variance. The variables are listed here. We have the problems with internal resistance because the best fit or the minimum value of residual variance was for internal resistance over 2.5 kilo ohms, while we know from the literature, from other investigations, that internal resistance of human body is much less. It's about 0.8 kilo ohms, and for this reason we limited the variation of internal resistance to this range, adapting the boundary confidence level. So it meant that the maximum value of internal resistance was just above 1 kilo ohm. The minimum value was just below 0.5 kilo ohms. So after this limitation, we found these variables, and these are the lines of approximation. The tests were conducted to maximum 80 volts touch voltage. Of course, it was for safety reasons. We extrapolated these values to higher voltages. These are values of body resistance up to 80 volts. After extrapolation for higher values, we obtained these lines. Of course, it's always difficult to test on live humans the higher voltages. It's difficult to find volunteers for this test. So, but the real danger, of course, is in this higher voltages. And this is the same for the touch current against touch voltage. And incorporating these curves into IEC time current zones, like here, these are well-known diagrams showing the effects of electric shock for different touch current and different electric shock. We obtained, and of course we have to take into account the fact that the resistance was measured along hand-to-hand pathway. The worst effects of electric shock, the ventricular fibrillation, is when the current flows from, for example, from hands to the feet. So we took into account the heart current factor 0.4, which means that the current pathway from the hand to the ground is about 2.5 more dangerous. We obtained the diagram of maximum shock duration against touch voltage for the hand-to-hand, left hand, right hand pathway. As you can see, this is in milliseconds. The voltage about for this blue line, the lowest body resistance, about 650 volts and 1 second. This is the maximum permissible shock time. Of course, for other subjects, this extrapolated curves were for higher voltages, but we always have to take into account the minimum body resistance. Okay, so let's go to the conclusions. We found out that the resistance of human body can be modeled using the impedance model proposed by Korniluk, and the analytical form was presented previously in the form of equations. Of course, we saw big differences between the models. They result from different physiological characteristics of test objects, of individuals. We extrapolated the experimental data to determine the human body resistance at higher voltages. It can be strange. We are talking about voltages of 600 volts, 1000 volts. Of course, the basic criterion we used was ventricular fibrillation. The touch current can cause, of course, other harmful effects, for example, burns, especially when the duration of the shock is much higher. So we cannot say that 650 volts for 1 second is completely safe. Of course, it's not. These experiments have been carried out in the laboratory. The conditions were good, the skin was dry. In environmental conditions, especially, for example, at underground coal mines, where it's a lot of heat and the humidity, the values of the body resistance, especially skin resistance, can be much lower. Of course, for different paths of touch current, effects can be different, and values of the body resistance can be different. The results we obtained can be useful for evaluation of requirements for protection means, and as I said, the next stage of research will be to find a model of human body impedance, this time for high frequency touch currents. That's all. Thank you very much.
I have a question. I'm sure that you know the IEC report effect of current to human beings and livestock part 1 and part 2. I'm sure that you compared your results with the results presented in this report. Could you indicate main differences between your results and results included in this report? The most important.
It's difficult to compare directly because we tested only 3 individuals, while this data in IEC report, especially the resistance versus voltage curve, have been carried out on much wider group, and there are some 3 curves I don't have now for different percentage of population. Our results were inside this curve, so there is no big differences, but as I said, it's only a preparation. This is the first stage of the work. We wanted to find a model, and now after confirming that this model is okay, we will use it for another research.
Thank you very much.
Thank you.
Yes,
Just a little question, was only comment. It's a very important thing, since nowadays, as you know, it is recommended to use in the home the 2 separate installations, one AC and another DC, since to avoid the losses due to converters, when you have, for example, the solar battery, something like that, to avoid the conversion from the DC to AC and supply directly the loads which is used for DC load, like lamps, something like the LEDs, something like this, that will be probably in the future, the old building, new building would be already equipped with 2 installations. Therefore, your work is of great importance.
Yes, so as I said, the DC applications are rising, and of course the hazards also will rise. Thank you very much.
Yes. Next presenter is from Czech Republic, Mr. Jakub Tal.
Good morning, gentlemen. The topic of my presentation is peak-to-peak current minimization by differential evolution optimization. My name is Jakub Tala, and I am from University of West Bohemia, from Department of Regional Innovation Center for Electrical Engineering, from Faculty of Electrical Engineering. This is my presentation outline. I will start with our research motivation, which was motivated by our customer requirements, which wants current source injector for automatic Peterson coil tuning. Then the presentation will continue with differential evolution optimization of injector reference current. Then I will present the simulation and experimental results, and finally I will talk about something about conclusions. So as I mentioned before, we have some customer which wants from us some current source injector for automatic Peterson coil tuning. This current source should have maximal amplitude of current of 5 amperes, root mean square, which should contain some preselected current frequencies, some preselected current harmonics for grid-to-ground impedance identification for automatic Petersen coil tuning. The other requirements from our customer was small series price lower than 1200 euros, small device volume lower than 6 liters, and also our current source injector should work to up to AC voltage 160 volts root mean square. The current frequencies range should be between 15 Hz to 130 Hz. So how does it look like? This is medium voltage network with lower voltage size connected in star. The central point of star is connected over Petersen coil to the grounding, and we are connected with our injector in parallel to auxiliary winding of the Petersen coil. This is our injector with filtering inductance, and we are measuring output injector current and output injector voltage, and we are calculating some admittances. I will talk about this in the next steps. Actually, the H-bridge inverter or injector is based on single-phase H-bridge inverter with fast IGBT transistors. Final application will consist of silicon carbide transistors. Filtering inductance is actually, and it should be also in the final application, 750 microhenry. And all switching frequency is up to average switching frequency, because we use analog hysteresis control of current, is around 80 kilohertz. So we have relatively large losses in the core of this filtering inductance, and our DC link capacitor is around 2 millifarads with 400 voltage on the DC side. Capacity, and we are control the DC voltage by there is not drone, but here is chopper which controls our DC voltage to 340 volts maximally. If there is some ground connection, we are switching off our injector, because it's not necessary to inject some harmonics to the grid network if there is any grid-to-ground connection, phase-to-ground connection. To minimize price and inverter volume, we focused also on peak-to-peak current, which was generated by our injector, and that's what is about our paper. So it was about minimization of peak-to-peak current, which affects mainly, of course, selection of transistors, and of course the core of filtering inductance. How does it work? We inject several harmonics, up to 12 harmonics simultaneously to the auxiliary winding of Petersen coil with the same amplitude, and if the Petersen coil is properly tuned and these harmonics are properly selected to be covered by this equation, we have the symmetric response. So this is results that injected currents with the same amplitudes and properly selected current harmonics will have the symmetric voltage response when the Petersen coil is properly tuned. So this is one possible solution how to tune the Petersen coil, by moving the core of the Petersen coil. Or we can use the direct computation method. We can, from two admittances computed from voltage and current, we can compute directly Petersen coil inductance, grid-to-ground capacity, or for example, grid-to-ground resistance. This is how our injector control and measurement scheme looks like. We have some processor. It's based on Texas Instruments processor with single point precision unit, F28335. We are measuring, as I mentioned before, output current and output voltage of inverter. Then these values are filtered by a low-pass first order butterworth filter, analog filters, and these values are measured by analog digital converters and by algorithm of by sliding DFT, sliding discrete Fourier transform. We compute the spectra of currents and of voltages, and we send these values to Peterson coil supervisor controller over RS485 bus. And the Peterson coil supervisor controller moves this Peterson core to achieve the resonance on 50 Hz with grid-to-ground capacity. As I mentioned before, the current of our injector is controlled by analog hysteresis controller, and the reference for analog injector for analog hysteresis controller was calculated from processor, and by digital analog converter is set it to hysteresis analog controller. So we inject up to 12 harmonics. As I mentioned before, we want to minimize peak-to-peak current. We use, this is a problem of global optimization in the real space. We are looking for the best phases of these harmonics to achieve minimal peak-to-peak. I will talk about it later. And for this real value problem, real value global optimization problem, we chose differential evolution, which is well-known method and very good method for real spaces problems. This is how the differential evolution works. We have some initial population. I will talk about these blocks later, but briefly, we have some initial population. We calculate the fitness evaluation. For us, it's peak-to-peak value. We select some possible candidates. We mutate them. We make some crossover and repeat this process several times. And after we find the best, we use the best founded values to use it for current generation. So this is a mathematical description of our problem. We have some of sinusoidals, and we are looking for thetas of the sinusoidals to achieve minimal peak-to-peak of course, for all time. We made the numerical approximation of this problem. So we minimized some, in our cases for 12 harmonics, we minimized 12 harmonics, 12 thetas. We are looking for 12 thetas which are minimizing peak-to-peak for some time with some discrete step calculation of this fitness function. And this fitness function is used for evaluated or results for our population of solutions. This is how the initial population looks like. We have some thetas randomly generated, and we calculate for them the fitness function. It was the first step. Then how the evolution looks like. When we took two random vectors of our solutions, we subtract them from each other, multiplied by some mutation constant, and added to some another random selected candidate, and this is our new candidate. The crossover is so this is how does it looks like. Or crossover, we select some parts or only some thetas which will change with the previous population, which will be changed only with previous populations, and then we make selection. If the new solution is better than the previous one, we change the previous solution with the new one. This is how our simulation results looks like. This is so we our signal, for example, in this case, contains 12 harmonics. This is the frequencies of our harmonics. Of course, the worst case when all harmonics has amplitude 1 was 12 amperes. With initial 0 phases for all these sinusoidals, the result will have 8.94 amperes, and after differential evolution optimization, the maximum peak amplitude was reduced to 4.62 amperes. So this is how the reference current looks like before optimization, and this is how the reference current looks like after optimization. This is how our progress looks like of the best maximal amplitude. How it takes approximately 4 minutes in the computer. We have also some simulation experimental results. Which was measured on Peterson coil, which was connected in parallel with capacitor. Peterson coil was tuned to 168 millihenries. It corresponds to 230 amperes, and parallel capacitor, which emulates the grid-to-ground capacitance, was 58 microfarads. Here you can see some results, how the converter voltage looks like. This is the blue one. Peterson coil primary voltage looks like. Peterson coil primary current is the pink one, and injector current is the green one. Injector current corresponds to our previously founded solution for optimal settings of current harmonics. This is how our voltage response looks like. So the Peterson coil is properly tuned in this case. The parallel resonance is the harmonics was the symmetry of voltage response was achieved, and how our injector current looks like. So this is we generate the constant current for all frequencies. So this is my conclusion. So the paper presents the new solution for automatic Peterson coil tuning. The paper was mainly focused on optimization of phases of reference current harmonics, which was generated by injector simultaneously. And these maximal peak currents play a key role in converter design, such as transistor selection, whole converter size and price, which we want to minimize. The maximal peak current for selected frequencies was reduced up to 2 times from initial set of harmonics phases, and the solution was programmed in Visual Studio C++ for customer usage. So that's everything from me.
In fact, we have no time for questions. Maybe on the one fast question. Yes?
I have a question concerning that you have used sliding window DFT. What is your experience regarding the accumulation of arithmetic error, and the second is the problem of stability of the sliding window DFT?
Yes, thank you for your question. It's an interesting question. We are using 2 separate sliding DFTs with 2 separate spectral components, and we are resetting which are working on the same frequency, and we are switching between them. And we firstly reset the first one. We are using the result from the second one. After some while, of course, during the time the errors are accumulated in the spectra, and we are resetting the second one, and we are using the results from the first one. So we are simultaneously changing these two signing DFTs.
Okay, thank you.
Thank you. The last presenter, not least, is from Latvia, Gennady Foresee. Please compress your presentation. It's not possible because thank you. Short time.
Thank you, Shaman. Good morning, dear colleagues. My work is called Problem of an Estimation of the One Generates Economic Efficiency in Latvia. This is not global problem, please don't wait on revolution, but every little problem is a problem when you must pay it. So, the aims of this research was to present a method for the wind turbine financial efficiency evaluation. At the main part, to define parameters that depend on this evaluation at particular case. This is microgrid with one wind turbine and some load and AC grid. So there are power relations. Wind turbine produce average power PW, average annual average power. The part of this power is consumed by load, annual average load power, and second part is can be transmitted to conventional AC grid. So what? Wind turbine producing average power is characterized with the capacity factor alpha, which is the ratio of average power to the rated one. Part of the average power should pass to the local grid consumers, an average consumed power of which can be characterized with indicator beta. So load average power divided by wind average power. Total construction price of wind power plant is C plant. So C kilowatt is installation outcomes of 1 kilowatt. Installed power of plant including power converters loss costs. K with index A, reduction factor for cost of installed power. So very simple. The annual financial efficiency in plant generation is here. So price of 1 kilowatt hour. There is outcomes for installation, coefficients, and capacity factor. So globally, dependence of an apparent price of wind generator power on the capacity factor and installation resistance is here. So it's very simple, but there is a problem with laws. How consumer can get compensation for power, for energy which is transmitted to conventional grid. In theory, it's possible to conduct net metering, or in other words, to transfer the produced electricity to the power network and use it again when it is required. Therefore, in Latvia is used a net payment system which is applied for microgenerators. In practice, the electricity costs for 1 kilowatt hour of each Latvian household consists of 3 main components. The distribution operator service CDOS, not a Microsoft DOS, just DOS. The mandatory procurement component CMPC, and the payment for the electricity CPE. Payment for electricity constitutes only 40% of the total cost for kilowatt hour. For household producing their own electricity from renewable source, it's possible to save on account of the last component. Each household must pay for operator service and MPC. 60% of the total cost for kilowatt hour. This payment depends on energy received from the conventional grid. So if you get something from conventional grid, you pay. Your payment will be greater than zero, not depending if you give your energy to conventional grid or not. Payment for the electricity is calculated by the net principle. So I called it E-balance, the amount of electrical energy for which household must pay in kilowatt hours. So it is difference from energy received from grid and energy transferred to the grid, or it is difference from between energy consumed by load and energy generated by the wind turbine. Total payment for electrical energy, DOS and MPC is so I called it for total equivalent amount of electrical energy equal, for which household must pay in kilowatt hours. And this E-balance, which is amount of energy for which we must pay, this amount of energy cannot be less than zero within 1 calendar year. Energy received from the grid is E load and C wind consumed. This is a wind turbine generated energy consumed by load directly without transferring to grid. And here is household payment estimation. So equivalent energy can be expressed as function of three variables: load energy, generated energy, and consumed wind energy. If we have a constant load, equivalent energy can be presented as function of two variables, only two. For simplification of the diagram, all parameters were specified to range from 0 to 1, and load consumes 1 kilowatt hour. So we can see this diagram. So what? If we produce 1 kilowatt hour of energy with our wind turbine, this generation can be passed when we need this energy for our loads, and when we give this energy to transfer to conventional grid. So our equivalent energy depends on wind. When we have sufficient wind speed for generation necessary amount of energy, we can introduce wind energy generation indicator, beta E, and next indicator, the wind energy direct utilization indicator, shows which part of generated by wind turbine energy is used by load directly without transferring to the grid. Consumed wind energy divided by generated wind energy. And this is this indicator used in diagram. Equivalent energy as function of generated wind energy and wind energy generation indicator. So dependence is not linear. So total equivalent amount of electrical energy for which household must pay depends on energy amount generated by wind turbine and energy amount used by consumer directly without transfer to a conventional grid. For modeling was used a load and wind process were used. So load consumes 2.1 kilowatt hour first or second wind profiles are the same according to energy, but not the same according to power. Third and fourth wind profiles are less than load profile, and next is greater than load profile, but not the same as moment power. Here is energy relations in the system at various wind profiles and constant load. We need one parameters, E equivalent. So if shortly we pay nothing, only in ideal case when consumed energy, wind energy divided by load energy is 1. When wind turbine completely covers load requirements in the same time when load needs the power. If beta E less than 1, in this case consumer can save on the account the rest of energy, but only within 1 calendar year. Therefore, this option creates obstacles for evaluation of wind turbine economic efficiency at long period, some years. The smallest equivalent energy value can be reached at the whenever possible bigger generated wind energy and directly consumed wind energy values. So conclusions. Annual cost and wind energy price depend on capacity factor as well on ratio of energy consumed by load to the energy generated by wind turbine. The amount of directly used wind energy depends on probabilistic distribution of the energy consumption and generation on the wind speed. Independence on conventional grid operator regulations and electric energy payment system, the owner of the wind turbine can get a compensation for energy transferred to the grid. But to describe the financial efficiency of the wind turbine, the indicator E equal was used. The smallest value of the equivalent energy can be reached at the maximum possible energy amount generated by wind turbine and energy amount directly consumed by load. To decrease household payments, it's possible to use load control. For example, some loads can be switched on when wind speed is sufficient for necessary energy generation. In each case, deep analysis on the household loads is needed. So, thank you for attention.
Thank you very much.
Maybe you can do something.
No question. The session is closed. Thank
Thank
very
you.
much.
Ladies and gentlemen, thank you for being here. We are in the second session 7A on Tuesday. We have 6 presentations. So each of you have about 13 minutes. So then we have a couple of minutes for questions. Then, well, my name is Alberto Rodriguez. I come from the University of Miguel Hernández in Spain. I will be glad to be your chairman. So the first presentation is round-trip delay estimation in OPC UA server client communications channel. Please, if the presenter is here.
Thank you, Mr. Chairman. Ladies and gentlemen, let me introduce our research titled, as was already said, round-trip delay estimation in OPC UA. I will tell a little bit what it is. Server-client communication channel. Before I start, I'm glad that this presentation to some extent resonates with the invited speech we had first day. The presenter talked about Internet of Things, and my presentation focused, of course, on much narrower issue, but it is directly related to telecommunications and round-trip delay as one of measures to estimate performance of what is achievable at nowadays technology. My presentation will include a little bit introduction of OPCUA protocol and its role in the Internet of Things. Then I will say several words about Internet of Things Gateway, which was developed at our department, and we use that equipment for experimenting and estimating that round-trip delay. Then the investigation itself and the results, including also a CPU load and impact of this communication on the CPU load. And at the end it turns out that it's one of the limiting factors as well, not only the infrastructure of networks, but as well as hardware capabilities of that device. And conclusions at the end. Also, I could add that this project was, on the device itself we developed, was at the beginning aimed for precision agriculture, which is the area of one of the areas where Internet of Things is expected and already playing a significant role. But later on we saw and find out that that device is not as much specific for agriculture applications. So therefore, from now I will talk about it in a rather general manner, because this could be applied to nearly all other fields of IoT applications. The general trend nowadays is that automation and information technology systems, they merge and the framework of Internet of Things. And on the field side we have a variety of industrial buses, heterogeneous local wireless networks, machinery, building automation, sensor networks, and so on. In the middle there we usually have this Internet of Things gateway, which ensures connectivity between these variety of networks in the field side and connects that to global communication networks, which are internet-based or 3G and 4G. And of course at the very end we have IT world, where cloud services, databases and other entities are located. So yes, the Internet of Things gateway, connectivity device between heterogeneous and IP-based networks, Internet protocol-based networks. Nowadays it works in IP4, but as we talked yesterday, IP6 is just around the corner. OPCUA server, or OPCUA protocol itself is quite a huge protocol. It takes its origins in automation world. It's open platform communication. At the beginning it was Microsoft protocol, and suitable for various Microsoft platforms, but nowadays it's turned unified automation, so platform independent. The protocol described in the OPCA or specified by OPCA Foundation, quite a big industrial consortium of big companies. The description of this protocol is really big, it's hundreds of pages. It's quite a complicated but rather sophisticated protocol. It can be attributed to such called system SOAP, service-oriented architectures. It ensures security, data modeling, and many things, which due to limited time I cannot present here. But that protocol is expected to play or also plays a significant role in the Internet of Things. And in our IoT gateway, this protocol is an application level protocol. And one of our aims or goals in this research to investigate how much it affects the round-trip delay, because end applications, they experience not only the network limitations, but the application level which we put on top of all network stacks. Shortly, this is the device. Because it definitely these parameters that we measure are influenced by the capabilities of hardware. I very shortly tell this. This is Cortex-A type processor from Texas Instruments with especially that type of or that size of clock frequency, some memories. To say this is a typical device, we could say this is a state of the art of today, maybe not tomorrow, but today is very typical, and the Texas Instruments itself declares that type of processors as very typical for devices like Internet of Things gateways. On the software level, this is run by or controlled by Linux operating system for the development of OPCUA server, because this device hosts server and clients connect. We use a commercial development kit. This is not the only on the market, but several can be obtained. They're quite costly, but in that project we were able to do that. Then it's an open VPN or virtual private network involved in the whole game in order to again control security issues and addresses for the device itself and clients that can connect to this. A short diagram of internal structure of software, which is the OPCUA server, then aggregation engine, and protocol adapters that are aimed to read data from a variety of these field networks. These could be CAN bus, these could be wireless networks, or even simple analog inputs, variety of possibilities. Then the goal of this research is to investigate round-trip delay. I say round-trip delay involves some characteristics of both yesterday mentioned key parameters that the customer is interested in, namely speed or transfer rate and delays, because in round-trip delay we send a request from the client, obtain the answer from server, and the client itself measures using its timers. As one timer mentioned, the client was running on the Microsoft Windows, and then it measures that parameter. This is the list of factors influencing round-trip delay. So the protocol itself, that application level protocol, a variety of settings, as this is quite a sophisticated protocol, settings that can be selected highly influence the throughput as well, performance of networks and protocols, and computing performance of target systems. The test methodology, there was not one single request and answer, but we approached it statistically. Every point in the charts I will show was acquired by sending 1,000 requests, and statistical estimates, histograms, and probability distribution functions were drawn out of that experimental data. And then CPU load also was observed internally in that IoT gateway and delivered to the client together with the answer, which delay was measured, but the answer included what was the current load of CPU of that gateway. Test cases were also defined. We were trying to generate variety of data. Sometimes we need only a single reading, so one node we send. Sometimes we need a group, 30 nodes, for example, retrieved from machinery buses, variety of parameters that are circulating in machinery buses. Some of these were sent in the maximum speed achievable by the hardware. Some were with specially introduced delays between requests, and this affects how the network, 3G network, behaves. Test environments were 3. In all environments, virtual private network was present in some communication layer. Then we tested pure Ethernet, then Wi-Fi, and finally 3G network. Maybe we don't go in detail in these drawings, but we have a gateway and remote clients. Of course, they are connected through some communication network infrastructure devices as well. And this is a 3G network involved. This is the way our results look like. More of them will be visible or presented in a paper that will be published at the end perhaps of this year. But there we have a round-trip delay and probability distribution function and cumulative distribution function, as it turns to present different aspects in a communication for the communication experts. But we see that this, in particular, this was 3G and VPN. We see really well dependent on scenarios. This is C and D scenarios. How much data in one packet we send, or do we introduce artificial delays like 5 seconds or not? These parameters are reflected in the obtained data. And we see really hundreds of milliseconds in 3G. And out of this data, one can project or predict, estimate what kind of applications that type of throughput can be suitable, especially if we want either to real-time control some remote machines or detect events or alarms that require some maybe immediate interaction or stop signals. So hundreds of milliseconds in a 3G network using that type of hardware and this type of networks. Then we saw or find out later, which was not at the very beginning, that quite a limiting factor was hardware capabilities of that IoT gateway. And then we estimated CPU load, which is provided by Linux utilities inside of that machine. Well, at the beginning when we saw these charts, visually they look like correlating. When we have a CPU load up to 100%, then we observed increase of round-trip delays. The way this is all these 1000 samples, and this is real time. But calculation of simple correlation did not show any significant relationship between these patterns, I would say, round-trip delay and CPU load. Perhaps because the CPU load estimation also was a little bit lagging on specific Linux implementation, So finally, to conclude, we were not able to declare that they correlate directly. But then from these patterns, we defined like a binary sequence where we accept some threshold. For example, that CPU load is 60% or 80% or 90%. These numbers are presented, 40, 50 and 60%. And on that other pattern, we define how many times the minimal round-trip delay is exceeded, either 5 times, 10 times or 20 times. So groups of then binary patterns were derived from these originally measured. And when we have binary patterns, we calculated the, in particular, Kulczynski-2 index, and there are a lot of other measures for estimating similarity of binary patterns. And when we calculated this, then it became obvious that they are correlated. So yes, and there was a hypothesis and conclusion that the larger are appearing peaks of round-trip delay pattern, the higher is probability they are due to increased load of CPU. So every time we have increased some number of times round-trip delay, they are probably due to CPU load, but not reverse. Sometimes we have seen CPU load increased, but that does not cause round-trip delay increase.
Please move forward.
Yes, I'm at the conclusions. So maybe some of them. In Wi-Fi and Ethernet-based networks, that OPCUA channel average achievable using this type of process, of course with a higher we can achieve higher, is in several milliseconds per one OPCUA node, which is one reading. Grouping OPCUA nodes is beneficial, especially in 3G networks, and the OPCUA channel was around 250 milliseconds, and dependent on how many nodes we group. And the last slide, in all networks, round-trip delay exhibited sporadic outliers exceeding average value up to more than 20 times, and we suspect that these outliers were caused by overload of CPU. Yeah, this was much higher when we reduced CPU frequency compared to the 800 megahertz. Finally, to conclude that OPCUA server is computational performance demanding application level and full speed interrogation that client is executed, then 800 megahertz ARM Cortex-A processor was just enough to handle server execution without affecting round-trip delay. So this was on the limits of the hardware capabilities. And then thank you for attention and any questions.
Is there any questions from the audience? Yeah.
Did I get you right that there was no wireless heterogeneous network involved, like ZigBee, Bluetooth, whatever, which is supposed to reach the endpoints in precise agriculture or Internet of Things?
Yes, that part is not included. We just investigated channel between IoT gateway and, let's say, cloud. And what is the delay between real end sensor to IoT gateway was not part of this investigation.
Have you done such investigation?
Not.
Okay. Any other question from the audience? Okay. Thank you very much. Thank you. And we move on to the next one, which is optimization of the design of multi-frequency annular arrays for very wideband operation.
Yeah, we'll use it. Okay.
Okay. Good morning. Thank you for the presentation, Alberto. So first thing is I would like to thank all those who make it possible for me to be here today in this beautiful country, in this nice place, and this interesting conference. So, as you say, my talk today is about the design of very wideband ultrasonic transducers. So I don't know if you are happy with the band, but there's a problem of bandwidth that we normally always have. So there are a few people in the world, there are strange people, they are narrowband people, and they're happy with a narrowband. So it's okay, there are some narrowband applications, but at least for me, I always need a wider band. The wider the band, the best. I don't know if this is the same for you, but at least for me it is. If this is for you, maybe you find something interesting here today. If not, well, sorry for that. Anyway, so I'm coming from Spain, from the Spanish National Research Council, which is the largest research institution, public research institution in Spain. And my co-worker here was Jorge Topete, who actually he should make this presentation. Okay, I'll try my best today, but okay, this is good. I will change. So this is the outline. First, I would like to give you the motivation of the work. I've said a few words about this, but a better introduction of the motivation. Then an introduction about multi-frequency arrays, some previous results, the optimization proposal I will to present here, some results, and finally conclusion, of course. So this is the. I don't know if this. Okay, that's good. This is a conventional ultrasonic transducer. Then you have a piezoelectric element here. This is in the thickness mode for longitudinal waves. So you normally have a piezoelectric element is here. You may have some matching layers. You may have a backing material, and then some kind of electrical matching network or built-in electronics, amplifier or something like this. And this is a typical response of the transducer when you use a spike excitation, for example. You have the signal in the time domain and then the frequency domain. This is the example of a 1 MHz coupled transducer made using a 1-3 connectivity piezoceramic. So this is a typical example of a transducer. So what means bandwidth in this context? So the larger the bandwidth we will have, this is the signal, the FFT. So we will have, if we have a larger bandwidth, we will be able to use more frequencies here, and the time and the duration of the pulse will be shorter. So it's important that we can define the bandwidth in two different ways. So normally we use the peak, and we take 6 dB below the peak, and we define this as the 6 dB band. But if we are interested in knowing how much energy can we use at different frequencies, maybe it is useful to have a different definition. It can be something like 20 dB above the level of noise. So, well, this would be a different definition, but anyway. So, wider bandwidth means shorter pulse and a larger working frequency range. Well, why are these two features of interest? Well, probably you already know, but if the pulse is shorter, I will have a better temporal resolution. So this is a conventional setup in ultrasonic application. You have a signal, you have different echoes. The echoes come from different places, and maybe they are very close together. And if they are very close, and then I need that the signal duration is very short, so that I can differentiate between these two echoes. And concerning frequency, if we have a wave propagating through a medium, and the medium is dispersive, but both velocity and attenuation will change with the frequency. And I can get a lot of information about the material if I am able to understand what is the variation of velocity and attenuation with the frequency. Okay, for example, if it is a proelastic medium, the attenuation will follow this law. If this is a fractional viscosity, a linear fractional viscosity is something like this. This will be linear viscosity, Rayleigh scattering, and relaxation. So this will be the different graphs, and if the bandwidth is large enough here, so I will be able to determine what is the dependency of the attenuation with the frequency, and I will be able to know what kind of material I'm dealing with. Good. This is an example. this is a tortuosity relaxation in a material like this, and you can see very clearly the evolution of both velocity and attenuation, and you can infer a lot of properties of the material here from this data. You have to solve this inverse problem, and you will be able to have a lot of properties. Look at the frequency range. We are going from 0.05 up to 5, so 2 orders of magnitude, a huge bandwidth what we need here, at least for an ultrasonic system. And well, how do we increase the bandwidth in a piezoelectric transducer? So we can act on the passive element, on the active elements, and in the electrical matching between the transducer and the electronics we are going to use. A passive element, we can introduce matching layers in a baking. Using a baking, you increase the 6 dB band, and using matching layer, what you can increase is this other band I mentioned to you before. This is the level of energy above the noise. So active materials. So we can use material here, piezoelectric material that present a larger bandwidth. And what are these materials? Piezo ceramic composites, the first solution, single crystals, and now we can use single crystal piezo composites, and we are getting bandwidths with these kind of materials above 100%, 6 dB bandwidth. Okay, but eventually we have a limit in the bandwidth, which is defined mainly by the piezoelectric element. This is the electrical impedance of this piezoelectric element, and the larger the separation between this peak and this peak, that means that you have the larger bandwidth because the electromechanical coupling is larger. And you can see that this here is the bulk ceramic, and the bandwidth is not very large. You can increase the bandwidth if you use a 1,3 ceramic composite, and you can even increase more the bandwidth if you use a single crystal. This is a PMPT single crystal piezo composite, and the bandwidth is larger in this case. Anyway, you always have a limit, a physical limit defined by the material, by the piezoelectric material that you are using. So this will be what we have with a monolithic transducer. We have the 2 peaks in the electrical impedance. You have a band that is related with the location of these 2 peaks. This band is larger here because we have put some matching layers in this case, and this is the typical field that you have with a transducer, this kind of transducer. So what we would like to do is we'll like to have several elements, different elements in the same transducer, so that each element works at one frequency. So eventually you can, have, this will be the band of one of the elements, will be the band of the other element, and so on. So eventually you will have a much larger bandwidth that you are obtaining by combining the bands of the different elements, so that you can get rid of this physical restriction on the bandwidth. So this is our solution. So we start with a 1,3 piezo composite disc. This is the composite. These are the electrodes, and then we machine 2 elements, something like this. And this element will have a lower frequency, and this one will have a larger frequency. And then we put the electrode we lost here, and this will be our configuration for an array with 2 elements and 2 different frequencies. And we are going to try to combine these 2 elements so that they work the way we want they work. So this will be a more detailed description. So you have the disk, the 2 elements, and this will be the radiating surface. We will put some matching layers here. You can put the packing here, and this will be the configuration of the electrodes on the connection. So this is a prototype. So the objective is to overlap the 2 frequency bands of the 2 elements, to overlap the 2 acoustic fields so that they are illuminating or insonificating the same part of the space, and also achieve a piston-like vibration of the surface so that we have a plane wave. So we'll be very happy if we can achieve all of them. So first, bandwidth. So this is the electrical impedance of the initial disk. We have the first resonance here, this is the second order one. And then when you produce this here, what you have is, this is the impedance of the outer disk, and this is the impedance of the inner disk, the outer ring and the inner disk. So you can see that you will have 2 frequencies, and they are not far away separated, and this will be the band of the of one of the elements. This will be the band of this element here, and you can combine both. Even better if you use two different pulsars, so you can match the electrical impedances accurately. You will have this band. It's an amazing band, 160% or so. So this will be very good. So the second thing that we wanted to do is to overlap the acoustic fields. So, and this is a measure. This will be the transducer, and we are measuring the acoustic field in this direction. When we use the outer lane, what you have is the field radiated here and the field radiated here, but finally they interact. This both field interacts in the region, and you have the maximum field here. So this is something like this. And if you do the map of the other element, you have something like this. And it's clear that if you use both, they will overlap, and they are both. So what we manage is we will have here in this region of the space the radiation of both elements, and we will combine here both frequencies. So in this part of the space, we will have this huge bandwidth I showed you before. And the last point is that we would like to have a piston-like vibration. So what we would like is that the surface vibrates as homogeneous as possible to produce a plane wave. So this is our initial configuration. In this case, I do not have experimental data. They are all simulation, finite element simulations. And what we're going to show you is the strain in the thickness direction. So the amplitude of the strain in the thickness direction. So if you can see here, this will be when we apply an electric field at this frequency, which is the resonant frequency of this element, and this is the distribution of the deformation. You can see that this element here is vibrating something like this. So we have a piston-like vibration, the one that we want. And we have almost nothing here, so we have almost no crosstalk between these two elements, which will be very, very good. But the situation is not so good here, because this element is affected by this one. They are connected, mechanically connected, because we didn't cut this part, and this huge part, this massive part of the transducer is affecting this one. So this part, this element is only free to vibrate here, and it's clamped here. So that means that we are losing this part of the element, and we are losing some energy and some amplitude. So what we would like to do is we would like to expand this region as much as this one here, so that we can effectively use this whole element in the transducer. So what is our proposal? Our proposal is to, using this finite element modeling, the idea is well, if we match the nodal planes, we have a nodal plane here, and we have a nodal plane here, but they are located at different heights. So the idea will be, if we match more or less these two nodal planes to the same location, probably we can improve the vibration here, and we don't disturb this much. So this is what we have done. So we have changed the relative location of this element within the transducer, so that to find out if in this case, which will be the case where all nodal planes are in the same plane, if by doing this we can improve the vibration of the surface. Okay. The first thing was to look at impedance, just to know if the bandwidth will be affected. And all the impedances of all these transducers seems very, very, very similar. You have only some variation in the direction here that seems to be due to variation of the radial modes that will be different in the different cases. But this is a minor difference. So from the bandwidth point of view, all these systems will be very, very similar. But we're interested in is in the vibration of the surface. How is the vibration of the surface? So this will be the first case when we put this, we displace this part downward, and then the next one is going to be a little bit up, and then we will go up. So if we go, you can see that this is not very good, because this part of the transducer is working not so well as before, and we didn't get much improvement here. If we move at the same, okay, no issues in that. So the point is that if we increase, it seems that this one is the best, because we have some interaction here produced by this mode here, and this is working not so good. And seems to be fine here. Not too worse here. But if we keep moving, then the situation gets very bad when we expect it to be very good, actually. So in this case, we have all nodal planes in the same situation, in the same location, but the vibration here is not better than it was here. But the problem is that the vibration here, as you can see, is much more worse in this case. It's strongly affected by the location of this element in this position. So, conclusions. So it is possible to use a multi-frequency array design with an annular design two elements and these two frequencies. The low frequency element is the outer ring. This is a curveless array and it's made of a 1-3 connectivity composite to avoid the coupling and the crosstalk between the elements. So with this design it is possible to combine the two frequency bands and achieve a huge bandwidth, in this case, a 160 band. This is a transducer whose center frequency is about 0.5 megahertz, and it goes from 0.2 up to 1, so it's huge. And we can focus the fields of both elements in the same region of the space, and we can be close to the piston-like radiation pattern using this configuration here, which has another advantage, is that we keep the integrity of the electrode, so we have not to replace this electrode. And well, the idea was matching nodal planes seems to be useless, because when you match the nodal planes, FEM simulations show that the vibration of the transducer is not as we expected. So, well, that's all.
Okay, thank you very much. Thomas, very nice presentation. Is there any question in the audience? Yes.
Thomas, what is 1/3 composite? Which direction is the cut?
1/3, what does it mean? In a composite, you have two phases. You have two materials. In this case, you have a piezoceramic and an epoxy, right? It's a material made of two materials, a composite. So these two numbers mean how many dimensions in the space are each phase connected. So 1, in this case, is for the ceramic. That means that ceramic is connected in only one dimension in the space. And 3 is for the epoxy. That means that the epoxy is connected in the 3 dimensions of the space. How we do this? This is a matrix of epoxy resin with some ceramic pillars on it. So the ceramic pillars, they are like cylinders, and they are connected in one direction. And the epoxy resin is a matrix that is connected in the 3 dimensions. So you can have a 2-2 connectivity, a 3-3, and
yeah, I understood that. But in final element modeling, it is not reflected.
In final element modeling, we use effective properties for that. Because it will be.
My idea was, if you go to the FEM results, the ones you consider the best. What if you cut the notch where you have those two disconnected?
If you cut here.
No, not through, but just a notch from the top.
Yeah, we should try that. But the idea was to, the idea not to cut, so to have a curveless array, was that it is much easier to produce.
Yeah, I understand, but this way you do not clamp the inner piston.
Yeah, that's right. So the other solution we will have a completely isolated elements and to fabricate both in separate and then put them all together. But
actually the structure of the piezo composite actually it does that because they are like pillars. So actually, there should be no clamping here.
Well, what you have is the coupling between the two elements through the epoxy. So another idea will be to use a softer epoxy for that. So the softer the epoxy, the lower this coupling, lateral coupling. So at the beginning, we hope that using a 1-3 connectivity transducer was enough to avoid this crosstalk here.
And if I can get one more.
We are running out of time, so
okay, so
we can discuss later. Okay. So thank you very much again, Thomas. Very nice presentation. So next presenter is a hybrid method for signaling transport of GMP LS control plane.
Well, dear Chairman, conference participants, my name is Suzana Miladic and I'm coming from Bosnia and Herzegovina, University of East Sarajevo, Department for Telecommunications Engineering. And in the next few minutes I'm going to present our paper, a hybrid method for signaling transport in GMPLS control plane, where we proposed one algorithm for optimal control plane establishing and performed some simulations to support our solution. The paper is organized in 6 sections, where we started with some related work in this field, then detailedly described our hybrid signaling transport method, performed some analysis using a network simulator tool, and discussed applicability of our method to multi-domain scenarios. It is well known that generalized multi-protocol label switching extends basic MPLS concepts, which have been developed for packet switch networks to make them appropriate for some systems with time division multiplexing, wavelength switching, or fiber switching in optical networks. We talk here about separation of control and data plane, which assumes different and appropriate routing and signaling protocols and some advanced possibilities for traffic engineering in optical networks. Signaling in control plane is needed to establish, maintain, modify, and terminate label switch paths in the data plane. These signaling messages are exchanged between software agents called signaling controllers. Since these signaling controllers are identified by IP addresses, we can say that control plane is actually an IP network. For signaling in GMPLS control planes, RSVPT protocol is adopted. So these signaling messages are exchanged and encapsulated in IP packets. Since mostly signaling requirements refer to low latency and high reliability, in our paper we proposed one hybrid method, which is some kind of compromise between these two requirements in optical networks. I will shortly talk about this related work, but first I'm going to say that there are 2 basic methods in optical networks for establishing control channels. The first one is in fiber out of band, EFOB method, and the second one is out of fiber method. What does it mean? In the first one we have data traffic and signaling traffic, and for each traffic we have assigned a different channel. But even these channels are separated, they are carried by the same physical path. And the characteristic of this second method, out of fiber, is that we have a completely different physical path for the signaling or control channel, and a completely different physical path for the data channel. So we have more pros in terms of reliability, network reliability. So in some previous works, authors compared these 2 methods, analyzing some of these issues. So we wanted to see what will happen if we combine these 2 methods in establishing control plane, and tested this method in terms of setup times. Now I'm going to describe this method we used. We observed the network standardly as an undirected graph with n nodes, e edges. This is the average node degree, which was calculated using this formula. Then we analyzed joint degree distribution. It's a probability that a randomly selected edge connects these nodes with these degrees. And on the right side, we have a total number of edges connecting these 2 nodes. The main idea of our proposal was that we built in signaling controllers in the nodes which have higher degrees, and the nodes which have lower degree, we make signaling through proxy routers, which are totally separate controllers. So we introduced here several parameters. This one is called node degree threshold, and it's higher than minimum and less than maximum node degree. So this parameter node degree threshold is important because actually this allows designer to flexibly plan and design a control plane and to make some compromise between latency and network reliability. Here we have a probability that a randomly selected link connects nodes with a node degree higher than this threshold, mark it with PF, and we at the beginning of the algorithm set this upper bound for probability. So using all these elements, these are some steps of our algorithm. At the beginning I said we set this upper bound, calculated node degree for each node, find minimum and maximum node degree, set the threshold and calculated this probability PEF. And the step 6, if we obtain this probability using the previous formula, less or equal to this upper bound, we place signaling controller at optical switch, or else we use a proxy router as some totally different router. This is one illustration of the method. We use the small network with 6 nodes. Here we calculate the node degree it was I think 2.67, and we put signaling controllers in these 3 nodes, and these nodes 1, 2 and 6 had less degree than the average, and so we put proxy routers A and B which manage to these 3 nodes. Also, this is one example of establishing a label switch pad between proxy A and B. When we have a service request, RSVPT message path is generated and it is received by our downstream router proxy B, generating this RSV message, and cross connection in the data plane is denoted with this command program XC. Here we started with the simulations. This was the first smaller one network where we using our method built in 6 signaling controllers and 4 proxy routers analyzing node degrees. And this was the second one, network with much more nodes. And we had built-in 9 signaling components. So for each of these networks we performed 3 simulations, as I said, using a network simulated tool and its associated tool for trace files, trace graph and trace visual analyzer. So these were the parameters of the first in-fiber out-of-band configuration, out-of-fiber, and our hybrid configuration, which assumes the previous, for this hybrid configuration, this was the control plane and for the second, and this was for the first network configuration. Average hop-by-hop delays between routers and between router signal controllers were 2.5 milliseconds, which includes propagation time, queuing delay, and packet processing time. The signaling protocol was simulated by a signal request response transaction with message of 1000 bytes. And since we supposed simultaneously establish paths, one bidirectional path between each pair of nodes, we obtained 66 and 190 for these 2 networks. Then these two formulas are related to the number of signaling messages. So this was the total number of signaling messages for the first and for the second network. And here we have the results, the three methods, and average and maximum setup time for the first and for the second network. Here we can say that these times obtained with the hybrid method are similar to these times obtained within fiber out of band method. And there are two main reasons because there is a reduction in these times comparing with this out of fiber method. First, reduction of delay is a consequence because we have a small number of routers and a small processing time. And the second one is the number of certain number of established paths, about 20% in our simulation, was established exactly in this hybrid method like in EFOB method. Here, these are the histograms of these obtained times and the number of established label switched paths for the first, second, and the third method, where we use this threshold 4 and obtain this value of probability. These were histograms for the first networks, and these are for the second network, the first method, the second, and the third method. And what is also important to say here, that we analyze what will happen if we use higher values of these node degree threshold in terms of average, maximum, and setup time, and in these values of probability. We can say that using higher values of these threshold, we obtain higher setup times. So the choice of this node degree threshold, as I mentioned before, reduces the latency or improves control plane reliability in terms of this probability or node degrees. So this is the problem of a network designer, and choosing this threshold, the designer is able to flexible planning or establishing optimal control plane solutions. Also, this is one section where we discussed applicability of our method to multi-domain scenarios, because it supports integration with algorithms where the interdomain path computing is used with the path computation element, and for scenarios where some domains are with distributed control plane like GMPLS, and the others are managed centralized, or they use centralized control plane. So the method is applicable also for this issue. And at the end, I would just say that our hybrid method is some kind of compromise between delay and probability that if failure occurs at the links which carries data and signaling traffic, and selection of this node degree threshold by a designer enables him to have a trade-off between these two requirements. And that's it.
Thank you very much. Very interesting presentation. Is there any question from the audience? Okay, so it was a very good presentation. So
thank you.
As we are trying to get the time again, so please, next presenter. It is electromagnetic compatibility analysis of DVB-T and LTE systems. I guess they are, yeah. It is the fourth.
Fourth, yes. dear colleagues. I would like to present, I'm Kęstutis Viskas from Vilnius University, and I would like to present the work of Vilnius University Telecommunications Research Group on topic electromagnetic compatibility analysis of DVB-T and LTE systems. My topic is organized as follows. A brief introduction, later describe system parameters and test bed, method of performance, also analytical methods, and at last results and conclusions. This work was mainly triggered by ITU decision to repurpose digital dividend 1 for telecommunications in Europe. Following this decision, Communications Regulatory Authority of Lithuania divided the band into six duplex bands for uplink and downlink communications. As consequence, electromagnetic interference possibilities appear when two systems operating in adjacency. So, in this work, we investigated DVB-T signal reception from LTE frequency division duplex downlink signal. In our test bed was set up in accordance with ECC report 1 with requirements. Input signals, input ports of DVB-T receivers were fed over wired environment through power combiner from DVB-T and LTE signal generators. These signals were measured at the input radio frequency input ports of DVB-T of amplifiers and filters. A measurement was we have a lot of measurements for different system parameter sets summarized in this table for different DVB-T signal modulation schemes, signal coding rates, signal powers with variations of LTE signal bandwidths and operating frequencies. So this table generated a huge amount of data and a lot of colors, and some of them I will present here. Talking about method of performance, there are a lot of criteria for evaluating interference impact. Ideally, a DVB-T receiver should be evaluated by observing bit error rate after convolution decoder or a number of transport stream errors, but such measurements are not possible because of commercially available DVB-T receivers lacks of such kind of ports. So instead of that, performance of DVB-T receivers was evaluated by observing picture failure events, which are defined as the number of visually observed picture artifacts during a certain period. We used 30 seconds. This is standard time. DVB-T receivers were quantified using two indicators, overload threshold and protection ratio. Overloading threshold is the power of adjacent channel interfering signal above which the receiver begins to respond non-linearly. It is interfering signal overloads the receiver. And protection ratio is the minimum signal to interference ratio required to achieve specified reception quality under specified conditions. So in practice, for every set of parameters, we determined maximum power of LTE interfering signal, and for every PLTE determinate signal to interference ratio. Analytical model of performance of evaluation is based on frequency-dependent rejection factor, defined in article by Quebler-Cameron. Qualitatively, this factor means power of interfering signal falling within the receiver part band. FDR is a function of frequency offset between center frequency of victim and interfering signals. And FDR are used spectrum masks for DVB-T and LTE. These are shown over here. Spectrum mask for LTE and DVB-T. Here we see these covers represent overloading threshold versus DVB-T signal power in receiver for 3 highest frequency TV channels, 58, 9, and 16. All of these covers show that show non-linear behavior of the receiver. We know we see that when we increase DVB-T, PLTE increases and reaches the threshold above which increasing wanted signal does not lead to increasing quality of reception. So from this we can conclude that LT base station operating frequencies closest to DVB-T band can cause strong DTT service quality degradations on these channels. Here we see resulting covers for protection ratio versus DVB-T frequency channel number. Here we see 7 covers, and the lower protection ratio means lower requirements from interfering signal and better reception conditions. The 3 covers on the top corresponds to 3 preamplifiers used connected to the input ports of the DVB-T receivers, and we can conclude that preamplifier gives worse conditions. It gives us a higher protection lower when comparing with the solid line, which corresponds to the case when no amplifier and no filter are used. And when connecting filters, we can only slightly improve reception conditions. So really it is only waste of money. And amplifiers are prohibited in this case. Here we see resulting curves which compare protection ratio measured in experiment and analytically calculated FDR values. These serpentine curves represent FDR values. We see that in both cases FDR calculated values and measured protection ratio values very good consigns. So in this case FDR function, we suppose that it could be used as indicator for characterization of protection ratio dependencies on frequency offset when estimating potential interference in U frequency bands when practical experiments data are not available. Here only repeated the 3 conclusions which are presented a bit earlier, so I will not repeat them. So thank you.
Okay, thank you very much. Is there any question? Yes, please.
Because I have 2 short questions, perhaps very light, simple questions. Perhaps in your analytical model, like function looks like cross correlation. It's a discrete version of cross correlation function. Is this correct? Your comment. The analytical model.
Yeah.
Yes, this one. Yes, that. After. This looks like cross correlation of these 2.
Maybe, but we found it quite suitable function for comparing experimental and.
Yeah, it's, I think it's the cross correlation of the signal LTE signal and DVB-T signal.
Yes.
Yes.
Signal.
And the second short question is, what is the physical reason for the interference? Maybe intermodulation contacts?
The physical reason of interference is the distance, channel edge distance between LTE and DVB-T.
Yes.
It's for 60 channel, it's only 1 megahertz, and for 59 megahertz, 9 megahertz. It's very closely.
But people sometimes say, I think that some people sometimes say about intermodulation products, you have non-linear operation of amplifiers, you have intermodulation, unwanted intermodulation signals, you know.
Maybe.
Okay, any other question? Then, well, thank you very much again.
Thank you.
We'll move forward to the next one, which is FPOPA pump phase modulation. polarization impact on generation of either components?
So, good day, dear ladies and gentlemen. My name is Sergei Svankins. I come from Riga, Latvia, from Riga Technical University, and today I'm going to present to you my research, which is called Fiber Optical Parametric Amplifier, Pump Phase Modulation, and Polarization Impact on Generation of Idler Spectral Components. Yeah, and to save time, we will straightly jump through into the motivation of the research. During recent years, the global internet traffic has been increasing rapidly. According to the latest Cisco forecast, by the end of 2020, the monthly globally transmitted IP traffic will reach 194.4 exabytes per month. Under the influence of this trend, optical transmission systems are moving to the focus of systems with wavelength division multiplexing, where for each channel there is a separate frequency used. In such systems, one of the main factors that limits transmission is optical signal attenuation. Therefore, amplification of the signal is required. The conventionally used erbium doped fiber amplifiers, if this trend will continue, will require replacement, as wider bandwidth in future will be used for transmission of the optical signal. Therefore, elements with higher optical insertion loss will be used, and therefore we need higher levels of amplification also. This is why, from this point of view, parametric amplifiers are a very interesting candidate, as this type of amplifiers can ensure broad, high level of amplification over a broad wavelength band. Amplification bandwidth up to 208 nanometers and 17 decibel has been demonstrated. But the most interesting fact about this type of amplifiers is that they not only can amplify the signal, but they also can be used for optical signal processing. For example, they can be used for dispersion compensation, wavelength conversion, all optical signal regeneration, time division multiplex, signal demultiplexation, and binary polarization shift keying to intense tone of keying modulation format conversion. 4 out of 5 of these possible uses require the usage of the so-called Idler spectral components. Here you can see a typical structure of a parametric amplifier. The optical radiation of powerful pumping radiation is being sent through a stimulated Brilliant scattering separation block, which is, in most cases, is a phase modulator, which broadens the spectrum of the pumping radiation, and afterwards is combined with the input signal. They together are being transmitted through a span of highly nonlinearity fiber, and at the output of this fiber, we obtain a combination of the pump, of the amplified signal, and of the Idler spectral component, which was generated while the signal and the pump were propagating along the HMLF. But unfortunately, there are also factors that highly limit transmission, that highly limits the performance of parametric amplifiers, such as polarization dependence of the gain, the relative intensity noise, which is being transferred from the pump to the amplified signal, and the already mentioned stimulated Brilliant scattering, which sends a major part of the pumping radiation into the backward direction in such a way it depletes the achievable level of amplification. All of these factors not only affect the amplification of the signal, but also affect the generation of the Idler spectral components. Therefore, the aim of this research was to investigate the impact of fiber optical parametric amplifier gain polarization dependence and applying pump phase modulation for stimulated Brilliant scattering mitigation on the process of generation of the Idlers. Yeah. In our first experiment, we have observed the dependence of Idler generation efficiency on the polarization mismatch between the signal and the pump. The following simulation scheme was used. Here you can see that the output of the standard 9 to 0 of keying transmitter was linearly polarized, and after processing through an optical attenuator, it was amplified by a parametric amplifier, the structure of which is shown below. So here, the radiation of the pump is being transmitted through a phase modulator in order to broaden the spectrum of the pump and therefore mitigate stimulative brilliance scattering. And afterwards, also its radiation was linearly polarized and then combined with the signal. After they both transmitted through a 1 kilometer long span of high nonlinearity fiber, at the end of which the pump was filtered out and the idler and the signal were divided among two receivers. Yeah. In order to ensure a certain mismatch in the states of polarizations of the initial signal and of the pump, polarization rotator was used. So here you can see the obtained results. Here you can see the dependence of the power of the signal and of the idler spatial component on the mutual mismatch of the states of polarizations of the signal and of the pump. As can be seen here, that when the states of polarizations of the signal and of the pump coincide, both the idler and the signal obtain their maximal power values at the output of the parametric amplifier. But when the signal and the pump are orthogonally polarized, both the signal and the idler experience their minimums. Polarization-dependent gain of 16.7 decibel was observed. It's the difference between the highest and the lowest value on this graph. And also it was found that 33.5 decibel difference in idler generation efficiency was observed in these two cases. The interesting thing is that theoretically, when this pump and the signal were orthogonally polarized, we shouldn't have observed any amplification at all, and the idler should not have been generated. But actually, in this case, we observed 1.6 decibel amplification, and idler with power minus 49.1 dBm was observed. This can be explained by the presence of the self-phase modulation, nonlinearity, and polarizational dispersion inside the high nonlinearity fiber while the signal is propagating along with the pump. This has caused a slight phase mismatch between the two components and resulted in also additional mismatch of the states of polarizations. Therefore, we could not maintain the orthogonal positioning of the states of polarizations of the signal and of the pump through the whole high nonlinearity fiber, which resulted in four-wave mixing, which eventually created 1.6 decibel amplification of the signal and generation of the idler. For a second experiment, the following simulation scheme was used. It's an 8-channel WDM transmission system with 50 GHz channel spacing and a parametric inline amplifier, which is placed here, the structure of which is identical to the structure in the previous scheme. The configuration of the pumping radiation is shown here, and the frequency tunes which were used to modulate the pumping radiation are shown here. They were chosen in a way to obtain maximal amplification at the output of the amplifier. The obtained results have shown that if we compare the signal at the output of the amplifier and the corresponding idler spectral component, we found that the idler obtained 54% spectral broadening in respect to the initial signal. This resulted in that all channels merged. This was detected at minus 15 decibel level from peak value. At first we wanted to measure it at minus 20, but it was not possible because the idlers actually merged and it didn't have minus 20 decibel level from peak value. So 54% spectral broadening was observed, which resulted in at least increase of beta ratio values by at least 3 orders for the idlers in respect to the signal at its initial frequency. Here are the main conclusions for this research. First of all, it was found that the process of generating the idlers was highly dependent on the state of polarization of the input signal. In our case, 33.5 decibel polarization dependence of the process was observed. Secondly, it was also found that when the signal and the idler were orthogonally polarized, the signal did obtain some amplification and the idler was generated. This was caused by the presence of sulfide ventilation and polarization mode dispersion, which resulted in additional mismatch of the states of polarizations between the signal and the pump. And finally, it was found that a pump phase modulation, which is used for mitigating stimulated Brillouin scattering in parametric amplifiers, results in broadening of the idler spectral components. This broadening has resulted in increase of beta ratio values, but by at least 3 orders in our case. So in systems where idler spectral components are used for all optical signal processing, while configuring, while choosing the frequency tones for modulating the phase of the pumping radiation, one must not only take into account the achievable level of amplification, but also needs to control the idler spectral broadening. Otherwise, we might just lose quality from the signal. And that's it. Thank you for your attention.
Okay. Thank you very much.
Maybe any questions
from the audience? Okay. So again, a very good presentation, very clear.
Thank you.
So we're going to move to the next one because lunch time is arriving. So the next and last one is on the transmission of global watermark image over vision FSO chip.
Hello, my name is Stefan Panic, I am from Serbia and I will present you this paper done by my group on the transmission of double watermarked image over Rician free space optic channel. Well, as you know, at the plenary session, the invited speaker said that the future of telecommunication is movement into higher speeds and movement into some sort of optical combining realization with standard telecommunications. And free space optics or visible light communication, as it is called in some literature, is some sort of upgrade of wireless communications and movement into the bandwidth that of visible light, 390 to 700 nanometers and maybe more, maybe 80 nanometers infrared, and maybe even in the bands of first and second optical windows. And this kind of communications can make speeds of about 50 or even 100 gigabits per second. And Wi-Fi is now going to be standardized with higher speeds than Wi-Fi, and grade of services and quality of services for Wi-Fi are under defining. And in some sort, this paper is motivated to exploit some grade of services and quality of services of FSO transmission that can be used in last mile realizations. And we have observed here transmission of watermarked image over Rician FSO channel. Watermark image is, as you all know, and it was also paper in yesterday in some session. Watermark is used when we want to insert some additional information in the signal, in the picture, maybe to prove ownership over some material, or to insert some copyright and in other needs. And we have in this paper we have analyzed the transmission of watermarked image and double watermarked image. We have inserted this is simulations. We have inserted 2 watermarks into some standard images, and we have analyzed the performances at the reception of this picture when it is transmitted to free space optic channel. Free space optic channel is modeled by Raysian model. This Raysian model is very general model that can be used not only not only for free space optic propagation modeling. And we have discussed, we have provided this performance analysis in the function of system parameters, and system parameter that is observed mainly is parameter k of this Raysian model. It is very important parameter, and this is some general stuff about watermarking and inserting hidden information and characteristics of digital watermarking and algorithms for inserting digital watermarking, as you know, are discrete cosinus transformation, discrete value transformation, singular value decomposition, and so on and so on. But the main idea here is to found the eigen values of the picture with this matrix, and then to add the eigen values of the watermarked image together. And then, as we know the eigenvalue of the picture, we can at the reception reconstruct this watermark. This is the main principle for watermarking, and singular value decomposition is used in our case. And as it has been said, free space optic has some very good performances, because we don't have interference with free space optics like we have in wireless communications, because every optical beam, two optical beams cannot cross and cannot mix informations, and this is the main good thing with free space optics. Then we have concentration power in near beam, then we have possibility of full duplex communication, then we have practical realization of free space optic system is also does not have very large complexity, but there are some also obstacles in free space optical communication. First of all, when this signal transmits through atmosphere, some wet parts of air or fog or something like that could cause that signal will the refraction index of the atmosphere will change, and signal would have some sort of scattering, and that would cause that irradiance will change in the space and in the time, and irradiance could be observed in such way as a random process. And also another drawback which wasn't mainly discussed in this paper is misalignment. The transmitter and the receiver should be very concentrated to avoid errors. And these disadvantages, as I said, are caused by turbulence, by sun, by fog, by rain, and so on and so on. And this change of irradiance and refractive index is also called scintillation. And we have observed this Raysian scintillation model, and we have observed the transmission of double watermarked image. And this is system model, how signal is transmitted. In the paper you have all parameters explained, so on and so on. And this is how information of signal at the reception can be presented. These are optical frequencies, phase, and this is the model of scintillation modeled by Ricean distribution. And we have 2 or 3 major parameters here, and the most important is K parameter. And K parameter is defined as this expression, and inside this expression we have we can define other system parameters like wavelength, then the refractive index structure, and propagation distance. All these parameters are in the parameter K. And this is how the signal at the reception looks like, and algorithm of simulation is explained in the paper. We have formed digital watermark image, and then we have applied, we have transmitted it through Raytheon channel, and we have applied some modulation, BDP-SK modulation, and after that we have done decoding, and when we have done decoding we then have made some comparations between original image and received image, and extract watermark and original watermark. Algorithms are explained in the paper and here in presentation, how we have inserted this watermark, primary and secondary watermark. These are the algorithm, also how primary and secondary watermark are extracted, and so on and so on. And we have observed peak SQNR and mean square error and normalized correlation and bit error rate. Those are 3 parameters that we have observed: normalized correlation, bit error rate, and peak SQNR in the function of parameters of optical link. These are watermark images that were inserted in the picture. These are pictures, standard pictures, in which we inserted these watermarks, and these are results obtained in the function of parameter K, peak SQNR, normalized correlation, bit error rate, and so on and so on. And we have derived some conclusions about K parameter values that should be used in order to achieve some required level of peak SQNR or normalized correlation or some required level of bit error rate at the reception. And if we want to have, I don't know, normalized correlation higher than 0.85 and peak SQNR bare values, we have here concluded that K parameter should have value higher than 4 decibels, and then here it is defined K parameter. K parameter is function of signal power, of wave number, of refractive index structure, of propagation distance, and we can in that way choose those system parameters to obtain this K value and to obtain this level of quality at the reception. And this is analysis for some, I don't know, last mile realization of free space optic transmission of the picture. Yeah. Thank you.
Okay, thank you very much. We are just in time. Any questions from the audience? Anything? So just a question, this key parameter,
Yes.
is it something you have developed for the measurement, or it is a standard quality parameter?
Well, we have done only simulations. We haven't measured anything yet. We are now buying the equipment, and we will try to measure. And this K parameter, it is theoretically defined how it depends on some parameters like the wavelength, then the distance between the apparatus, then the refraction index, and so on and so on. And this is only simulations in MATLAB. And when we provide the measurements, I hope it will be soon, we will see how is this in practice like it was in MATLAB.
Thank you very much again.
Thank you.
So just to remind you that we have lunch from now up to 13:30 and at 4. At